Hey everybody, this is Mr. Lowry. This right here is the assignment that we started in class, and we did a lot of this as a group. We did it, the first couple proofs together, went over them together, and then students finished it in groups as well. So if you're at home or if you didn't finish this in class, this will kind of help you get the rest of the way there. So we got a couple theorems to prove and some corollaries as well. The thing about these proofs here is that they require some what we call constructions. And so we talked a little bit about that in class today. The first theorem that we're going to prove is this guy called the isosceles triangle theorem. Now if you're not sure what an isosceles triangle is, or if you can't remember, we can review that really quick. There's three kinds of triangles based on their length of their sides. So we have what we call a scalene, which is where none of the sides are congruent to any of the other sides. You have isosceles, which is where two of the sides are congruent to each other, and you can have like a really wide one, or you can have like a little narrow one. That's called isosceles. Ooh, that's hard to spell. I think it's got an S and a C in there. Isosceles triangle, and then of course we have what we call an equilateral triangle. Okay, so if you're not sure, about those terms or whatever, they're going to be part of your assignment today. You can find them in your book. You can start by looking them up in the glossary or in the index and trying to find them. I'm trying to find the page for you right now. Sorry, hang on a second. Thought I had them. I think it's at the very beginning of chapter 4. There we go. Sorry about that. Okay, got them. So page 179, this is page 179, you can know what those three different kinds of triangles are. So these terms are going to be important today. You got isosceles, equilateral, and scalene. That's on 179. Okay, so this theorem is about isosceles triangles, and this guy is on page 216. Okay, and this is what it looks like. It says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. Now notice, if you have two sides of a triangle congruent to each other, you essentially have an isosceles triangle. Okay, so what it's saying is, sorry, gotta pick up the camera here. If these two sides are congruent, that's isosceles, right? Two sides are congruent. Then the angles that are opposite of them, or like across the triangle from them, are congruent as well. And sometimes this theorem is called the base angles theorem in other textbooks. So you can see that these are called base angles here. So all this is good information about isosceles triangles. If you weren't here today, it'd be good to go through that page. Okay, so just for a reference, this is on page 216. All right, so we're going to write a proof for the isosceles triangle theorem. Now, it actually turns out that this proof's in your textbook. It's right here. Okay, and so I'm not going to write it all the way out for you. You can kind of get it from here. But I did want to talk about how we use constructions to help. Okay, so in this case, we're starting with an isosceles triangle. So notice the given is that we have this triangle PQR, and what we're going to assume is that PQ is congruent to RQ. So these are the two sides that are congruent that make it an isosceles triangle. Okay. Now the first two things here are kind of weird. Like it doesn't start with the given, which it probably should. The other thing here is it's like defining other points and drawing extra lines. And you might wonder, like, why is that okay? Like, how is that even allowed? Well, we did some constructions not too long ago in class, and we can use those constructions in our proof. So those constructions are perpendicular bisector. So if you remember, we took our little compass, and we did two arcs, and we found out where they overlapped, and we cut that in half, and that gave us a perpendicular bisector. Now, perpendicular means creates a right angle. So when we create a perpendicular bisector, we're not only creating a right angle, we're also creating a midpoint. And every segment will have a midpoint. We can do this to any segment. So one of the things we showed with our construction was that we can create a midpoint using this construction. Right? You get a little extra, but that's kind of what we got. The other constructions we talked about were angle bisector, which was a similar idea. We cut the angle in half. So when we have an angle bisector, we get two congruent angles. We have a segment bisector, we get two congruent segments. And the other one we did was where we copied an angle, and if we copy an angle in the right spot, we actually get parallel lines as well. So the three big ones were perpendicular bisector, angle bisector, and then we talked about how to copy an angle. And the fourth kind of bonus one was parallel lines comes from copy an angle. Midpoint and right angle come from the perpendicular bisector. So those are the constructions we can do, which means we can add these things to our picture. We can add midpoints, right angles, we can add parallel lines, we can add angle bisectors. We just have to do it like one thing at a time, and we can't assume too much about that shape. So when we look at this proof over here, what we have is S is the midpoint of PR, right? So you're like, well, how can you just add a midpoint? Well, remember that our perpendicular bisector allows us to add midpoints, okay? And every segment has one midpoint. Okay, then what it does is it connects S to Q, the midpoint of the triangle, to the bottom, I guess, of the triangle here. And that's going to give you a line, okay? Now, what we can assume is that S is the midpoint, which gives us, you know, these two segments equal to each other. We can't necessarily assume that this is a right angle or that these angles are the same. That's not really part of the proof. So that's kind of where we start, all right? But from there, we get this segment congruent to this guy. We already know that this segment is congruent to itself because of the reflexive property, and then these two sides are actually congruent to each other because it's an isosceles triangle. So that was part of the given. So these two sides are congruent to each other given. These two are congruent to each other because of the definition of midpoint and the midpoint that we constructed. And then this side's congruent to itself. So altogether, that gives us side, 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 which means we can say these two triangles are congruent. And if the triangles are congruent, then the angles, P and R, have to be congruent to each other as well. Okay, that's by CP/CTC. Remember, if two triangles are congruent, then all their parts, corresponding parts, are congruent as well. So that's the first proof here. You're going to write that out here, okay, the proof of the isosceles triangle theorem. The reason why I wanted to just give you a little bit background is I wanted to, again, explain to you what isosceles means, and also talk to you about how we can add things. Like this is called an auxiliary segment. Like, how can we add an extra segment? How are we allowed to just add a midpoint, right? It all comes back to constructions that we talked about. Okay. Now the next theorem in your book is actually this theorem. If two angles of a triangle are congruent, then the sides opposite of those angles are congruent. So notice that we actually are starting with the angles and saying if the angles are congruent, then the sides opposite must be congruent. So this is actually the converse of the isosceles triangles theorem. Okay? So 4.9 is the isosceles triangle theorem. 4.10 is its converse, and you don't even have to really look in the book to get this one. You can just reverse the original statement. So coming back here, this is the isosceles triangle theorem. The given part, the if part, is this guy. We got two sides congruent. The then part is that we have two angles that are congruent. Okay, so this is the Q. In a converse statement, what we do is reverse the P and the Q. We like change the order of them, and that's going to give our converse statement. So our converse statement would say something like, if the angles of if two angles of a triangle are congruent, then the sides opposite those angles are congruent, which is what it says. So if you want to, you can go in here. This is actually on page 218, and you can write that down there, but you actually don't need to. As long as you know what a converse is, you can just write it from the original. So I'll kind of leave that up to you. Okay, now for the proof of this, we're going to actually end up doing another construction. So I'm going to kind of run you through that guy really quick. We are going to start with an isosceles triangle. And actually, we don't know it's isosceles yet, but we're going to draw one that looks isosceles. We're actually going to prove that it's isosceles in a second. So let's start with something like this. Doesn't have to be perfect, but I'm just trying to make it look kind of isosceles here. Okay. I'm going to label the points, and you can label them however you want. Okay. Then we're also going to assume that these are congruent. So the converse, if you remember, I didn't write it down. You're going to do that, but it's right here on page 218. If two angles of a triangle are congruent, then the sides opposite of those angles are congruent. And again, that's the converse of the isosceles triangle theorem. Now I just drew my figure a little bit differently. Doesn't really matter how you draw it, so I'm going to start this way. And the given for me here is I'm going to assume that angle A is congruent to angle C, and I'm going to prove that segment AB is congruent to segment CB. Okay. Now what this is going to require is it's going to require another construction. Okay. In this case, what we're going to do is we're going to create an angle bisector, which was one of the things on our list. Remember, for every angle, there's an angle bisector, a segment or a ray that cuts it into two congruent angles. And we showed how to construct that without any specific angle measurements. So this angle, ABC, is going to have an angle bisector that cuts it in half. And so I'm just going to draw that right here. Okay? And I'm going to name this point D. Now, we have to be really careful here when we use a construction to not assume too much. Okay? So what I know is this is an angle bisector, and that's going to basically tell me that these are congruent to each other. But I don't know that this is a right angle. I don't know that this is the midpoint of AD because we didn't construct a perpendicular bisector. We constructed an angle bisector. So I have no idea about these two angles, this one and this one. I have no idea. I don't know anything about this segment and this segment, but it actually turns out that I don't really need that. If you kind of look at what I have so far, I have angle, 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 and then the triangles share this side. So I'm actually going to have congruent triangles by angle, angle side here. So let's start writing out our proof. We kind of know where we're headed now. Let's make it a little bit more formal. So S for statements, R for reasons. I'm going to start with my given that angle A is congruent to angle C. And that is given. And I'm also just going to construct BD array to bisect angle ABC. Now in your book, I think the postulate they use there is the protractor postulate, which basically says that any angle has a specific measurement, and if you have a specific measurement, of course, you can cut it in half. I'm just going to say by construction because we talked a little bit more in detail about those constructions and when you can make them. Okay, so any angle has a bisector, and you can construct it. We showed that with compass and straight edge not too long ago. Okay, so now what we have here is that the measure of angle ABD, that's this guy, is congruent to the measure of angle CBD, and we know that because of the definition of angle bisector. Okay? All right, so we got angle, angle. We're going to talk about our side now. So step 4, we're going to say BD is congruent to itself, and that is the reflexive property we've been using. And in this case, we're talking about congruent segments. Reflexive property of congruent segments. All right, now the whole point of all that stuff was to actually show two triangles are congruent. ABD is congruent to CBD. Sorry, I'm going to say triangle CBD. We know that by angle, angle, side. So now we can finally conclude that if these two triangles are congruent, then all their corresponding parts are congruent. So remember that there's minimum information we need to show two triangles are congruent. In this case, we use angle, angle, side. But once we have the two triangles that are congruent, we get all the other pieces, right? So we know now that we've actually concluded it, we can now say that these two segments are congruent, and these two segments are congruent. And we actually know that these two angles now are congruent. We didn't know that before, but as soon as we have the triangles are congruent, all the other pieces fall into place. So we know that segment AB, which is this side of the triangle, is congruent to its corresponding part on the other triangle, which would be CB, which actually shows that these two sides of the isosceles triangle are congruent. Now we actually know it's an isosceles triangle. Okay, so if two of the angles of the triangle are congruent, then basically we can cut this triangle in half to get two congruent triangles, which will show that these two sides are the same, which will prove that it's an isosceles triangle, basically. All right, so that's your proof there, okay? All right, now, one thing we have to talk about is we have to talk about what a kind of a corollary is. Let's go back just a little bit and let's talk about isosceles triangles really quick. So I'm heading back to that page I showed you earlier. It's the very beginning of chapter 4, this guy. So notice that the way that isosceles is defined is at least two sides of an isosceles triangle are congruent. And here it says all sides of an equilateral triangle are congruent. So notice that all equilateral triangles have at least two sides congruent, which makes an equilateral triangle a special kind of isosceles triangle. Okay? So when we proved theorems about isosceles triangles, we can kind of apply those theorems to equilateral triangles as well. We basically get some ideas as a bonus. So if you go back over to page 218, you will see these two what we call corollaries. Okay? And a corollary is essentially a theorem. It's like a mini theorem. And it's kind of like a bonus theorem. It comes as like a result of something else. Okay? So you got corollary 4.3 and 4.4. Okay? You're going to write both of these down in your assignment. And I wanted to talk a little bit about this language, if and only if. Okay? The if and only if basically means that it works both ways. When you see that if and only if, it means it's a biconditional statement. A biconditional statement is a statement that works both ways. So as a review, I put a page number on your assignment there. You can go back to page 81, which talks about biconditional statements. So it says, both the conditional and the converse are true. The conjunction of two statements is called a biconditional. So when a conditional and its converse are true, you can write it as a single statement using these words if and only if. Okay? So when you look at the wording here on corollary 4.3, it says a triangle is equilateral if and only if it is equal angular. Okay, equal angular just means equal angles. All the angles are equal. So if all the sides are equal to each other, then all the angles must be as well. But remember, this is if and only if, so it goes both ways. So what you're going to do here is you're going to write down that corollary. Okay. The if and only if part means it's a biconditional statement, which means it works in both directions. And then you're going to write down those two conditional statements. In other words, you're going to write this both ways. If it's equilateral, then it's equal angular. If it's equal angular, then it's equilateral. Okay, those are the two different ways. So start by assuming if it's equilateral, then it's equal angular. If it's equal angular, then it's equilateral. So we take a biconditional statement, which means that it has an if and only if, it works in both directions, and then we can write it both ways. Okay, got another corollary here, 4.4. That all of the measures of an equilateral triangle are 60. You're actually going to prove that. We're going to come back in the next video and talk about that proof together because we're just kind of running out of time in this video. So tune in for the next video where we'll talk about the proof for 4.4 and get started on your homework.